Well, our last speaker, unfortunately, things didn't work out, so we couldn't have him. We really would like to have him back again, and so we'll work on that. We'll see if we can get him booked as soon as possible. Lou Tancredi, though, had reached out to me not too long ago and had a suggestion about a guy that he had met that he knew that he goes, he would be a great speaker. So it just so happened that that happened like a day before it looked like our other speaker wasn't going to be able to make it. So boy, talk about falling on the grenade. So I was almost Richard John Wright III, and they ended up calling me Dan Wright. But so our name, not my namesake, but Richard S. Wright Jr. is our speaker tonight. He's a contributing editor for Sky and Telescope. And he's been a serious imager for over 2 decades. Now, by trade, Richard is a computer graphics and imaging specialist and works full-time at Lunar G Inc. And that's on some of the world's most advanced GPUs and graphics software technologies. Now, in the past, he's worked at Starry Night. He spent nearly 20 years as a consulting engineer and imaging evangelist for Software Bisque as well. He continues consulting with vendors in the astronomy industry and product development by his own company, Starstone Software. And you can also visit his web gallery too. That's www.eveningshow.com. So please welcome for the first time the Westport Astronomical Society's live online science lecture series, Richard Wright Jr. Welcome.
Thank you. Thank you for having me tonight. Let me share my screen and start my presentation. So this is the future of astrophotography. So we're going to talk about kind of how we got where we are today and where we're going. And I hope you'll enjoy it. We'll have some question time at the end as well. So, a good place to start is in the beginning. In the beginning, all we had was our eyes to observe the heavens, and we built tools to help us. We figured out a lot of things with before the telescope, did math, figured out cycles and found patterns, but we were still limited by what we could observe with our naked eye. Then about 400 years ago, the telescope came along and we amplified our eyes, and a revolution was had in our understanding. Hang on a second, I'm going to adjust this a little bit. There we go. No, it's hiding my notes. There we go. There we go. It's important to remember about this revolution with telescopes that it made a lot of people uncomfortable because they like things the way they were. People don't like change. It makes a lot of people uncomfortable, and it always will. And over my tenure as an astrophotographer, I've seen a lot of changes, and it is funny how things even today change makes people very uncomfortable. So we made bigger and bigger telescopes, which made it possible to see things we never imagined. We charted the skies in unprecedented detail, mapped the moon, studied how the sun's surface worked, and the large telescope and the human eye ruled scientific discovery for a couple of centuries. Then came photography. Appropriately enough, it was an astronomer who coined the term photography in 1839, Johann Heinrich von Madler. What a name. He combined photo from the Greek word for light and graphy, meaning to write. And astronomers quickly embraced the use of photographic plates because of their good resolution and ability to make images. Louis Daguerre, I never could say this word. I've heard it said so many times. It's French. Daguerre. Louis Daguerre himself is believed to be the first person to take a photograph of the moon. However, it was in January of 1839. Unfortunately, a few months later, his laboratory burnt to the ground, and we don't have any copies of it. Henry Draper in March of 1840 took the first ever photograph of the moon, at least the first photograph that remains today. It was also a daguerreotype. And later that year, Henry Draper also took a picture of the Orion Nebula. This is not that different from my very first Orion Nebula picture, to tell the truth. Andrew Carlisle, only a few years later, was taking exposures that could record stars and nebula that were invisible to the human eye. And things were about to change big time. For the first time, photography was showing things that the human eye had never been able to see, even in the largest telescopes. This is an 1840 photograph of the Orion Nebula. I think that is just that just boggles my mind. Before long, we were using glass plates, and they were the state of the art. It was in a lot of you know the story. You know, October 1923, Edwin Hubble took this famous photograph of the Andromeda galaxy, and he was like, "There's a nova. That's not a nova. That's a variable star. It's a Cepheid variable star." And we know things about Cepheid variable stars, and we can use them to gauge distances. And we had a variable star in another galaxy, and this was a breakthrough that allowed us to calculate the distance to the Andromeda galaxy, proving without a doubt that it was indeed a separate galaxy from our own. Before that, galaxies were nebula too. We didn't know that they were individual whole galaxies. It's worth pointing out that Henrietta Swan Leavitt, who's the discoverer of Cepheid variables and their nature, and they could be used to measure distances. I mean, important woman in astronomy. Many people would assume she stayed in the kitchen and made sandwiches. Imagine we would still not know how big the universe was today if that were the case. Okay, so here's one of my favorite photographs. I was helping out at a science fair in North Carolina, and this place called Perry, Pisgah Astronomical Research Institute. They had a glass plate archive there, which is archives glass plates from all over the country. They've been collecting them and trying to preserve them and scan them for posterity. And they had it was a science fair, but also like an expo sort of thing. And they were showing off these glass plates, and you had a little loop to look at them. And I saw this little galaxy pair, NGC 5427 and 5426. And I'm like, oh, that's a cute little interacting galaxy pair. I'm going to go home and take a photograph of that. It took me a year before I got around to photographing it. But I went home and I photographed it. And that photograph is on the right-hand side. That's about a 10-year-old photograph for me. It was 10 years ago that I took that. But I find these two pictures side by side to be a really powerful example of how far we've come. The glass plate was taken in March of 1977. Millions of dollars of equipment on a carefully chosen mountaintop. And 1977 was not that long ago. If you're young, you're probably like, oh, that's a long time ago. That was 2 months before Star Wars came out in theaters. When Star Wars was in theaters, this is how we were taking this was state-of-the-art astrophotography at a commercial, at a big professional observatory. The image on the right, 10 years ago by me, a CCD camera and a Celestron telescope. The whole pile costs a couple of $1,000s. And I took it in the middle of a field in Okeechobee, Florida, where Lewis, by the way, has his setup now down in Florida. And I think that's it's staggering how far we've come in that short amount of time, really. And to think about where we'll be, 50 years from now, astrophotography wise. Interesting. So in our own lifetimes, we've seen a lot of, incredible leaps. I remember when I do remember the digital to chemical revolution. I'm just old enough. I started astrophotography taking pictures of the moon with a film camera. I was a coward. I never did that long auto guiding in the dark with gas hybrid film and that sort of thing. But the moon is really bright, and if you have a big enough telescope, any idiot can shoot the moon, right? Even with film. But we made that transition to digital. A guy in Florida named Don Parker started using webcams to image Jupiter and Mars, and people were like, "You thinking this is ridiculous? This can't be done." Now, lucky imaging is it's a thing. People do it all the time with dedicated cameras. Even putting a laptop next to your telescope. I remember, I worked at Software Abyss for 20 years, and those guys have been around a lot longer, and they used to tell me stories. And the very first advanced imaging conference, they were mocked. They were like, you can put this software on your laptop, sit it next to your telescope and control the camera. And they were just mocked. They were like, nobody's going to take their laptop outside and sit next to the telescope to take pictures. What are you, crazy? But it caught on. And this pattern is not going to stop. And we're in the midst of a lot of change right now. A lot of, to some people, very uncomfortable change. But we're in the middle of a lot of change now, and it's going to keep changing. For a long time, we had to expose for a long period of time. Any given exposure had to be long enough to where the light hitting the film it would collect enough to activate the film, or the light hitting the CCD sensor or whatever kind of camera you were using would introduce enough electrical potential in the sensor to get above all the other sorts of noise that are available on the sensor. But guiding has always been a thing, all the way back in the Hubble days. They set up in that cage and they looked through an eyepiece and kept the star in the reticle to keep it where it was. I have friends younger than me who've been doing astrophotography longer than I have, who sat out in their backyard and hand guided with a little joystick on their telescope. And then ESPIC came along once we started having electronic imagers, and they weren't the first ones to do it, but they were the first ones to have a commercially successful auto guider. And it would watch a star, and as the star drifted, it would bump the telescope to keep that star centered, and then the main camera could expose for a long period of time on that, on your main target. I'll talk some more about guiding in a few minutes. Other things that are going on: CMOS versus CCD. By the way, that game is over. It wasn't that long ago I was giving talks about how CMOS is catching up with CCD. Well, they've lapped CCD now, at least commercially available CCDs. There's some fans watching this now in the audience, or they'll watch the video later and they'll be like, oh no, you can get a CCD from Teledyne and blah, 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 blah. I'm talking about commercially available. I didn't have to mortgage my house. I've got a camera and commercially widespread available mainstream cameras. Modern CMOS cameras, the latest generation of CMOS, totally trump CCD in almost every way. Their quantum efficiency is getting better and better. It's already approaching 100%. A lot of them are in the 90s, and that's, another generation or two of CMOS that they're going to be, very close to 100. Read noise is approaching 0. It's never going to get to 0. I know that, but it is getting awfully close to 0, getting much, much smaller every generation that's doing that. They're highly linear. All the amp glow we used to complain about is gone. By the way, it wasn't actually amp glow. CCDs had amp glow. CMOS was actually something else. We just called it amp glow because that's, never mind. We can talk about that in the Q&A later if you want. Tiny pixels don't have very full well capacity. Yes, they do. They do now. Modern manufacturing techniques, tiny pixels have very deep full well capacities, like you used to have big pixel CCDs and the pattern noise is becoming almost negligible on that. Now, I want to point out something about the camera industry. This is a very uncomfortable truth. If I was a comedian on stage, I might put it this way, but when it comes to astrophotography, nobody actually cares about us. When it comes to cameras, what's driving all of this is cell phones, security cameras, all those stoplight cameras, all those cameras that are taking pictures of your license plate when you drive on the toll road in the dark, low light, fast photography with low noise. That's a multi-trillion-dollar industry. And the truth is we're downstream from that, and we're benefiting from that. But that's what's driving all of this technology forward. I don't want anybody to think that the quest for the perfect astronomy camera is what Sony is driving at. No, Sony is driving at better security cameras, and sometimes their sensors work out to be really good astronomy camera sensors as well. And that's what's pushing all this forward. And what's going to keep pushing it forward even more for another, I don't know how long CMOS technology will last until we come up with something completely new and novel. But I would imagine, CCDs had a run for a couple of decades. CMOS will probably have a run for a couple of decades as well. Now, it's not just about cameras. Glass is getting better too. This was my Officina Stellare Veloce. And this was the most expensive thing I'd ever bought in my life other than a house and a car. Okay. And actually, the car, my wife always got the car. So this is the most expensive thing I'd ever bought for myself in my life at the time. And when I bought this, it was an 8-inch f3 telescope. And it was like being 16 and having a Ferrari, or like, if you've seen Ferris Bueller, having that, that red Ferrari and driving around. When I showed up at a star party, I was big man on campus. It's like, oh, Richard Wright's here and he's got the Veloce. We got to go see the Veloce. This is so cool. And it's a sexy beast of a scope. It's a beautiful, beautiful scope. F3, but it's not as impressive as it was. If I bring it out now, it's like, oh, that's a classic. That's nice. Show me your f1.4 Sigma tripod lens that'll shoot the Milky Way in 8 seconds on a tripod with no tracking. That's what I want to see. F4 is the new normal now for Newtonians. I remember when I got my first F4 Newtonian, people were like, oh, Richard, you got to be careful at F4. Whew, those things are hard to collimate. Man, F4 is a challenge. Nobody cares anymore. F4 is sort of like if you bought a Newtonian, it's not F4. It's like, well, you might make up some excuse for why you got one that was, only F6 or F7. But, F4 is sort of the new normal. A lot of refractors are starting in the F5s and F6s now, not at F10. So F3, also F3 reducers are common. I have 3 scopes now that'll shoot at F3. I take that back. If you count 3.F4, 5, I have 4 scopes now that'll shoot in the F3s. So it's not that big a deal as it used to be. And F2 is even a commodity with the RASA. By the way, I should interject here. What is this F number? Just in case you don't know what that is. The focal ratio, the smaller the number, it's the ratio of how much light the camera is, your lens is collecting to how small of an image it is. It's actually the aperture divided, the focal length divided by the aperture. But really, if you want to visualize it geometrically and realize what it's doing, it's collecting a big bunch of light and focusing it to a very small area. And the lower that number, the bigger the ratio between how big the opening is and how small your image is, which means it's focusing all that light down and you're getting a lot of light in a very small area. And that makes for very fast photography. We get a lot of light very fast. We can get a well-exposed image in smaller amount of time. So focal ratios are getting better. Optics are getting better. Cameras are getting insanely great. What's next? Where we are right now is pretty darn good. But optics are crazy fast. What happens when everybody's shooting at F2 and they're easy to collimate and it's not that big of trouble, to do, when cameras can't get any better, when we're almost at 100% QE and the read noise is negligible, the process we're doing now really can't be improved anymore. That's it. We're out of room. Well, we could guide better. You're missing the point. We could eliminate periodic error. You're missing the point. We got mount modeling. Again, you're missing the point. We already have all of those things. And they're not really going to make a really good camera any better than it already is. So these are only marginally improving the existing process. And so what's going to happen is we're going to have to change the process. The process itself is going to change. Now, this is, by the way, my opinion. I've been following technology for almost all my life, working in the technology industry. And I have been so lucky so many times. And I think I'm going to be lucky about this too, as far as how things are changing. And I think by the time I'm done with the talk, you'll agree that I'm probably on the right track. it's pretty obvious where things are going to be going. I'm going to make my other prediction. This is like the biggest disruptive thing I think is going to happen. Maybe that's a little overstating it, but I think auto guiding for long single exposures will be dead in the near future. I think it's actually already dead most of the time, and we don't even know it. Cameras are already better than we think they are, and we're still doing things the old way because we don't know any better. Imagine a guy who fell out of a time warp and he gets a brand new big giant Ford monster pickup, and he insists on putting a mule on the front of the pickup to haul it around. I think that's what we're doing sometimes when we're auto guiding or when we're following advice that made a lot of sense in 1992, but don't necessarily make as much sense now. The future of technology does not always look like what we expect either. A lot of times criticism and fear of change is really the lack of our imagination. This is a magazine cover from 1981. I have this magazine. Maybe it will make me rich one day. No, it won't. But it's a 1981 Byte magazine. And what about, a computer on your watch? Wouldn't that be cool? What would it look like? Well, it would look like a tiny computer on your wrist, right? It would have a CRT display, just like I think of, and it would have a little tiny floppy and a little tiny keyboard. Well, here's my smartwatch. More power than sent men to the moon, when I was a small child. And so a lot of times we're stuck on what I'm doing now is the best way to do this. How can I make the way I'm doing it now even better and better? We get to a point where how I'm doing it now can't get any better. You can't make a camera more sensitive than 100% quantum efficiency. It's not going to collect more light than is coming from the object. And you can't get the read noise down below where it doesn't matter anymore. So how are we going to improve the process? So my specialty when my bio was being read was I work at a company called Lunar G. And even before I went to work at Software Bisque, I was doing computer graphics technologies. So my technical expertise is using computers to make pictures. And so here's your next buzzword: computational photography. You're welcome. This is going to be the buzzword people are going to be talking about they already are really to some degree. What is computational photography? It's basically a computer assisted photography. And what this means is it's not like gathering the data and then processing it with PixInsight or something later. This is where your processing adjustments are made on the fly automatically. And you're already doing that. You've been enjoying this for years. If you have a camera with autofocus, that's computational photography. Cameras do color balance internally. I can take my phone and swipe it across the Grand Canyon, and it will live, while the video is recording, it will live stitch a panorama while I watch. That's a lot of computer power in a phone. High dynamic range, where it'll take a bright image and a dark image and combine the two together. And it does that right in the camera. Your phone will do that. My DSLR will do that. Focus stacking, taking multiple images at different focal depths and then combining them so that the entire depth of the scene is in focus. All of that is computational photography. All of that is done in camera today. I joined a local camera club for a while back. I like doing daytime photography, and I wanted to become a better daytime photographer. And so I went because I was like, all right, I know how to use my camera. I know about ISO and focal ratios and stuff. I need to learn the art of photography. I need to learn about, lighting and composition. And, I've read some good books on the topic, but I just want to get there. And they have these photo competitions. And what came up over and over and over again was a lot of the gripe about the camera competitions. You get this in astrophotography too, is you shouldn't be judged on your processing skills. You should be judged on what comes out of the camera, because what comes out of the camera is really more honest. And I really only have one response to that, which is simply that you have no idea what comes out of a camera anymore. Back in the day when we used film to take pictures, we would take our film to Kmart or the little photo booth in the parking lot. And you know what they did with the film? They processed it. That's right. They processed your film to get an image out of it. And if you wanted really good pictures, you took it to a processing house that was good at processing. Okay. And it would make a difference to where you took your pictures, because they would develop it and they would enhance it a little bit. They would saturate it. They would work on the color. They would do some things to it in order to get a really good image. Some of the processes that we use today in Photoshop that we take for granted were invented by people like Ansel Adams in a darkroom. Plus, if you saw what comes out of a camera, it's actually horrible. This parrot picture isn't even that accurate. The left side of this parrot picture would be black and white, and it would look like a screen curtain, because what comes out of the camera is not even it's not even color image. It's a monochrome sensor with color filters and a little pattern over it. And then a computer algorithm interpolates and fills in the gaps and creates that image for you. So now, instead of a technician processing your film images, a computer processes your digital images and outputs it. Your phone does it, your camera does it. Even when you shoot raw on your DSLR or SLR or mirrorless, and you bring it into Photoshop or Adobe Raw and it shows a nice pretty picture, you're not actually looking at what the image looked like off the sensor. It's done all sorts of things to that image before it displays it on the screen. You got to go really out of your way to see what the raw data actually looks like. You can use PixInsight to do it, but you got to turn off a bunch of things so that PixInsight shows you the raw image. Okay, so what is my point about this, other than, I'm not trying to pick on anybody. The same thing is going to happen with astrophotography. Right now, the best astrophotographers in the world have their own dark rooms, metaphorically speaking. They take their pictures, they bring it into PixInsight, they bring it into Photoshop, and they spend 20 hours or 40 hours processing their data, and they get a beautiful, APOD or something at the end of the day. And we're seeing this transition now to where, though, it's getting easier and easier to do what they used to have to do in the darkroom, or what they used to have to do with PixInsight and that. And the cameras and the technology is going to put out images that already look pretty good. And you're going to do what I do to this parrot. I'm going to tweak the saturation a little bit. When you look at the parrot and then you take the picture of the parrot, you got to bump the saturation. This is another thing. People saturate their pictures for astrophotography. Don't oversaturate. It's a valid criticism to say don't push the saturation, but I've heard many people say you shouldn't push the saturation at all. No, I wouldn't take a picture of a bird without pushing the saturation a little bit. And if you look at the image and you look at the bird, you'll see the image is not as saturated as the naked eye image is. But anyway, I digress. Where are we? Graphics processing unit. This is the tactical warhead in the battle of image processing. There's such a thing as a graphics processing unit. You've heard of the CPU, central processing unit. This is what does instructions and moves memory around in your computer and figures out your bank balance and things like that. This is called a GPU, graphics processing unit. So it's the same, but graphics oriented, highly parallel. What does that mean? One of my favorite Disney characters, not one of my very favorite Disney character, is the Sorcerer's Apprentice. I love this story and I love this part of Fantasia. If you've never heard of it, Mickey was an apprentice to a sorcerer, and his job was to clean up or something. And he casts a spell on a broom, sweep up and bring the water. And the broom was bringing the water, and the broom, too much water. So he couldn't turn the broom off. So he chopped up the broom with the axe, and the broom turned into a whole bunch of brooms. And then all the brooms were bringing water. And the next thing you know, there's a whole flood because all these brooms are bringing water, and you can't turn that off. Imagine you're painting a fence, takes you all day. 2 people can paint a fence in half a day. 4 people can paint a fence in a quarter of a day. Imagine how fast you could paint a fence if you had 1,000 people painting that fence at the same time. That's what you get with the GPU. Each pixel can have its own CPU, so to speak, and you can write little programs that will work on just one pixel. And then you can have hundreds and thousands of those programs running all at the same time, each one working on an individual pixel. And so this is tremendously fast as far as it processing images. If you've got a really fast computer with 8 cores, I got an Alienware laptop. It's a gaming machine. It's got 8 latest Intel, i7, whatever, and it's got 8 CPU cores. And a lot of image processing software today will use, those 8 cores. Well, that's cute because you can do 8 things at a time with an 8-core CPU, but a GPU has thousands of cores. They don't run as fast as the CPU, but you have thousands of them. So it's like it's like those videos you watched when you were in middle school where the ants would eat up a carcass. If you've got enough of those little ants working on that carcass, you're going to have nothing but a skeleton very, very quickly. And a GPU makes short work of graphics processing tasks. Here's a couple examples. The ASI Air has a GPU in it. I don't actually know that they're using the GPU. I think they're only using the CPU on it, but they're everywhere. The top picture is an Arsenal. It's a little add-on for your DSLR or SLR. It has a GPU in it, and it does panoramas and high dynamic range and focus stacking. It does all these sorts of things, and it does it just like that because it has a little GPU built into it. 10 years ago, I gave a presentation at the Apple Developers Conference. I was the first person to use a GPU to compute asteroid orbits. So I wasn't just computing things like per pixel. Each asteroid had its own processor on the GPU, and it would process its position in the solar system. And bam, the entire Minor Planet Center catalog would solve simultaneously at once. And we could display that on the screen. It looked like a donut-shaped snowball blizzard in space with the asteroids all flying around as we sped up the time. So GPUs can do a lot of things. And a lot of software developers in the astronomy business and astrophotography are figuring that out and are making use of GPU technology already. And that's only going to improve as we roll down the road. So live stacking. A lot of you have heard of this. Live stacking is where the camera takes a bunch of short exposures and stacks them live while you watch. And we know this is great for outreach. We can put something on a target, and in 5 minutes you get this image of the target, and people get, the general public gets really excited about it. But the serious astrophotographers all know that you can't do real photography with live stacking, right? It's got its limits versus really long exposure. Well, I'm here to tell you that is about to get turned around. It's actually already getting turned around already. So live stacking is already here. Most smartphones do it. I can actually take a picture of the Milky Way with my iPhone. I can walk my neighborhood at night and hold my phone still, and it'll take several dozen very, very short exposures, combine them all while I watch, and I'll get a very nice low noise image on my cell phone. If I can do that on my cell phone, why can't I do that with astrophotography? We've had some products that do this marketing trick, by the way. There's nothing.
You're breaking up.
Them in the SkyX. SharpCap does it. PixInsight does it. This is where often the Malincam crowd gets irritable, justifiably so. If you're a Malincam guy, we didn't invent EAA, but you guys have been doing this for a while. But the digital resolution is catching up with you. If you want to look at it that way, that would be fair. We have whole telescopes devoted to that. The Unistellar. Stellina. These things are just live stacking in a box. ZWO has C-Star. There's something called the Dwarf. I just saw something 2 or 3 days ago, something new on Kickstarter. Everybody's doing this. I swear there's a new live stacking telescope that's coming out, every couple of months. There's some live stacking stuff, and I know a couple of them that I've talked to people about, and other vendors, and have done some consulting with. There's more stuff coming, still along these lines. But as I said a few minutes ago, we all know, right, that live stacking can't compete with the way we've been doing, the serious people, the way we do astrophotography. But we know that this happens with all technology. Anything that's crude and expensive initially ends up amazing and cheap, in just a few years. And so the core question is, can live stacking really match today's rigorous long exposure approach? And the answer is yes, Virginia. Yes, it can. It's already pretty good, and I think in one more generation of sensors, it's going to be the end of long exposure, photography. Completely. My favorite Merlin from the best Excalibur movie that predates probably a lot of people watching this. But my favorite quote from Arthur C. Clarke: "Any sufficiently advanced technology is indistinguishable from magic." Uh, but Merlin would be the first to tell you there's no such thing as a free lunch. You make a deal with the dragon, you got to pay up somewhere. So all this CPU magic and machine learning and AI, it's fake, right? It's just going to do fake. It's just going to be filling in the gaps with fake stuff. I'm not talking about that. That's a real thing. And that's also going to happen. I don't know how that's going to play out. It's not my area of expertise, but that's not what I'm talking about. I'm talking about doing real photography, getting real data, and it's not magic. It's science and it's physics. So the science of stacking and physics of light play an important role here. And cameras are reaching a milestone that's really important that we might not realize is happening. So let's talk about the fundamentals of stacking before I try to convince you of anything else. So here's a nice whirlpool galaxy on the left. You've got a noisy image. On the right, you've got a much cleaner image. And it's like one exposure, and then you stack a bunch of them and you get a cleaner exposure. It's very, very important that the exposures be different exposures, because that noise you see on the left is random. You can't take one noisy image and multiply it, stack it on top of itself and get a cleaner image. You're just going to get the same image over and over again. So the noise has got to be random. And then when you average them or sum them together, same net effect, you get a much cleaner image on the right side. The goal here is not to suddenly make the image brighter by combining all these images, but to get the noise down, or more accurately, get the signal to noise ratio down. Because every time you add an image, the noise and the signal both increase, but the signal increases faster than the noise increases. And that's how we get this win. We get to where the beautiful image swamps the noise down at the bottom when you combined enough of these images. Here's a graph. The first time I was introduced to stacking, I was shown this graph, and they were like, all right, so here's what stacking does. Let me get my mouse over here and pretend I'm the professor from 20 years ago. Every image you add, the noise goes down. So as it's 1 over the square root of the signal. And so, when you take about 12 images, you notice that line's not getting any lower. And so after about 12 images, you're not getting any real benefit from going longer. So don't take too many images. And I'm like, okay, great. And I probably went on for a few years before one day I went, don't take more than 12 images. Well, is that 6-second images or 60-second images or 5-minute images or 10-minute images? Wouldn't that make a difference? Well, of course it makes a difference. And this chart was made by someone who probably did not get a good grade in algebra. Here's a much better chart. Signal goes up with time. And the straight line here is the signal. The signal just goes up and up and up the longer you expose. And how fast that goes up is based on not only how long you're exposing, but it also is based on how bright the object is. It's also based on how big your aperture is as to how much light is being concentrated on your sensor. Signal is signal, not number of exposures. Signal is not even time. Signal is signal. If you think about the physics of this, how bright, how many photons are showing up, the more photons, the more signal. That's what this line represents. And the noise is the square root of that signal. And you can see the signal goes up very fast and the noise does not go up very fast. It doesn't matter how many exposures you take. It matters how much signal you're getting. Very, very little signal down here. The noise is greater than the signal and you probably can't even see anything. It's just complete noise on the screen. Then finally the signal starts to pop out above the noise and you can see more and more. And the more signal you get, the better and the cleaner your image is going to be. If you shoot the core of the Andromeda galaxy, you probably only need one exposure to get all the signal you need for a nice clean image. Just like if you shoot a parrot at the zoo in the daytime, you get lots of signal. You don't really need to take a whole bunch of images and stack them. But in the dark in my neighborhood, I need to take a bunch of images on my phone and combine them to get the signal to noise ratio to be better. When I'm shooting at the Horsehead Nebula, I need to take lots of images and combine them to get lots of signal. And it's very important to realize this photo in the background is a good example. There are areas of this photo that are very bright and the signal is going to be very strong and the signal to noise ratio is going to be low and it's going to be very clean. But all this gunk down here at the bottom, am I pointing there? Yes. All this gunk down here at the bottom, 10 years ago, everybody's Horsehead Nebula, down here, it was all dark and there were just stars. Nowadays, most people's photos, you see all these clouds and things, and you can see stuff going on in there. There's detail going on in there. Why is that? Because the signal to noise ratio has improved so much over the last 10 years because of either better optics, faster optics, or better camera technology that they're bringing out all those details that you couldn't see. Now, there are limits to stacking. Can I just take 1 second exposures, for example? Why don't I just take, 100 million 1 second exposures? People have done that, and it does work. However, there are trade-offs. You have to take a lot more 1 second exposures than if you had just taken 5-minute exposures. So how do you know where in there is the maximum or the shortest exposure you can actually get away with? There's only so much light arriving at your target either. Nothing's going to change this unless we use AI to fake our pictures. If you need 3 hours of data to get a good deep image, you're still going to need 3 hours of data no matter how long your exposures are. You still need that total integration time. In fact, the word integration implies that exposures can be infinitesimally small. It's just math. But we have something called theory and we have something called practice. So the math describes the physics. The physics does not obey the math. So what is the limit then? How do I know how short my exposures can be? Or why can't I just do 1/10 of a second exposures on and on and on? And the limit is the noise from the camera. Cameras introduce a lot of noise into our individual sub-images. We have read noise, which is the standard electronic noise just from converting photons into electrical signal into digital numbers that our computer can manipulate. There's some fluctuations that are going on there. There's dark signal non-uniformity, or basically dark current noise. Photoresponse non-uniformity, which is another type of variation between pixels. These noise elements, if your signal is so faint, it's down here bouncing around where this noise is, you can't pull the signal out of that noise very easily. You can eventually, but you have to have a prohibitive number of exposures. But once the signal you're looking for gets above those noise thresholds, then you can stop. If the signal you're looking for is above those noise thresholds, if you can get there in 5 seconds, you can stop at 5 seconds. If it takes 30 seconds, you can stop at 30 seconds. So it depends a lot on the target that you're shooting, whether you're doing, sulfur or nitrogen narrowband filtering, on the focal ratio of your telescope, things like that. But the root physics is the signal, the limit of stacking is the signal has to be above the noise. That's always been the case. That's not something new. In fact, this is why we used to guide. So auto guiding, here's two pictures of two different auto guiding setups. So you have two telescopes, your main imager with the camera and a smaller imager with the camera. And it would, one could be piggyback, or you could use one of these little mirror things, pick off axis, and then have a mirror up, camera up above it. And then you would use the sky or PhD guiding or something like that. And it would tweak the mount to follow the star as it drifted. You might not be perfectly polar aligned, or your telescope may sag a little bit as it tracks across the sky. And this corrects for all of that. It keeps your telescope pointed where you need it to be pointed, so you can leave the shutter open for a long period of time. And a good auto guide graph usually looks something like this. If you're not quite on the pole, you get a little push in one direction on declination. The right ascension, the RA gear tend to, it would speed up and slow down ever so gently based on all the mechanics. And so, you would follow all that to get a very long exposure. But things have changed. Auto guiding was invented when we were shooting on glass plates. And auto guiding was invented, when we were shooting with CCDs that had read noise in the 20s and 30s of electrons. Just going back into my history of astrophotography, the ST9 is 13 electrons of read noise. We got down the last couple of generations of CCDs, the Trius 694, probably the Sony 694, I think, is like the last great CCD. But it had, in a good implementation, it had 3 electrons of read noise. Most CMOS cameras now, if you're shooting at high conversion gain, even if you're not pushing it all the way to 1 electron, you're shooting at 2 electrons of read noise. And that's tremendous. That's tremendous. Now, pattern noise, okay, to be honest, CMOS has been here for a while, but we still couldn't get away with real short exposures with CMOS cameras with low read noise, because they had low read noise, and the marketing department went, they have low read noise, we have an advantage on CCD. We're going to print this on the boxes, and we're going to talk about how low our read noise was. But most engineers were just seething because the pattern noise on CMOS sensors was so bad. And this is why CMOS got cheap and the read noise got really low. And we were all like, it's still not as good as CCD. And people are like, the read noise is lower and I only paid $500. Shut up. All right, I'm happy. It's not as good as a CCD. And the reason they weren't as good is because they had really bad dark pattern noise. So even though the read noise was very low, it still had some pattern noise down in the low end. And that pattern noise moved around. It wasn't consistent, which means you couldn't calibrate it out. So even with the first couple of generations of CMOS sensors with low read noise, the noise at the bottom of the signal well was still very bad. And you still had to expose long enough to get your signal above that noise floor. However, starting with, I think the IMX 455, Sony's 455 sensor, is probably the first widely available CMOS sensor with low read noise and low pattern noise, and was actually linear enough to be useful for science and for taking proper flats, and it had good control of the glow around it. Since the 455s come out, Sony's been releasing, the 571, the smaller version of that, the 533, 585, all of the latest, greatest CMOS sensors from Sony all have perishingly small read noise and perishingly small dark pattern noise. And that's dramatically dropped the floor of how short you can go on exposures. And, 1 or 2 more generations of sensors, that threshold is going to drop to where it's just a couple of seconds of exposure time. And so, I used to go around saying all the time, guiding needs to die. Now, this was a hard thing to preach when I worked at Software Bisque, because they made $10,000 mounts that would track and you didn't need to guide. And I was like, no, you don't need to guide because you don't need to expose that long. And the last two CCD chips I shot with is the 16200 and the 694. And those sensors had read noise low enough. I only needed to go a couple of minutes on anything. And that includes narrowband. The problem with the 16200 was it took 10 seconds to download an image. So if you're only taking 30 seconds or 1 minute exposures and then you burn 10 seconds every time you downloaded one, it was, we call that the duty pattern. It was better to take longer exposures just because you were wasting a lot of time downloading instead of exposing. Okay, so if I've convinced you that you can get away with, a minute or two now and a few seconds in the future, you would be right to say, okay, yeah, but there's still some drawbacks to use these short exposures. As the electronic noise goes away, there's some challenges. So what are they? Storage and processing space. You can live stack. Okay, storage and okay, I'm getting a little excited, so I'm ahead of myself. I don't want to read my slides, but I'm very excited about this. I get ahead of myself. So storage and processing space. Okay, where am I going to put 10,000 exposures on my computer? I'm going to download all those 10,000 exposures, and then I'm going to let PixInsight run for 6.5 days while it aligns them and it stacks them. So obviously something's got to change, and that's what I was talking about at the beginning. We have to change the process. First, you're going to take your darks or biases at the very beginning, probably biases. I think darks are about dead. Most cameras, there's almost no dark current. When you cool them, all you need is a bias. By the way, no matter what you're using, CCD or CMOS, don't take a bias and a dark. The bias signal is in the dark. You're actually double calibrating if you put a bias. You're double calibrating and you're adding noise. But that's another talk. Where was I? Take your biases and your flats before you image, okay? And then you live stack. You calibrate on the fly and you live stack. And you don't save every single image. You just save, you could save the final product, but let's be realistic. You don't want to image, you don't want to live stack for 6 hours. So you're going to save, you're going to live stack for 5 minutes at a time or for 10 minutes at a time. You're still going to get 5 minute and 10 minute subs. But you've got a 5 minute live stack sub and another 5 minute live stack sub and another 5 minute live stack sub. You can guide between these very short images, or you can just let the scope drift. And then every 5 minutes when you save the intermediate result, you move the scope. Because early, when I first started talking about this, people were like, if you don't guide, you can't dither. Yes, you can. Dither, just all you have to do is move the scope every now and then. And it doesn't have to be every single exposure. It just needs to be enough times that you can come up with a statistical rejection. A dozen times is enough. As long as it's, I probably shouldn't get too far into that. You can dither without guiding. Let's just say that. The software people will figure it out. We can dither without guiding. Don't worry. Or, even if we're guiding and we're taking 1 second exposures, we don't have to dither between every 1 second exposures. Okay. It will work. So what's going to solve the storage and processing space? Live stacking, computational photography. We're going to do all this stuff on the fly. The duty cycle, again, how are we going to get away with the 1 second exposure, a second to download? Now it takes twice the time. So we need a fast camera. Cameras are plenty fast. I have an APS-C sensor that I can do 15 frames per second. It's not going to be a problem, even on a large sensor. What about residual pattern noise that may be left? We can get rid of that with computational photography. We can apply image processing techniques to get rid of that as well. So, things change. Here's a picture of my first hard drive, ST125 Seagate. Who remembers these? I'm not in a live audience. You can't. Okay, I see one hand there. Yeah. All right. I remember $500. $500 for, I think it was 40 megabytes. And this wasn't my first one. It was my second one. My first hard drive was 20 megabytes. I had to get the 40 megabyte because I got the newest Borland C++ compiler, and the compiler wouldn't fit on my hard drive. And imagine a 40 megabyte hard drive. One photo from my Canon EOS RA would not fit on that hard drive. That's how far we've come in relatively short period of time. So I'm talking about things, this isn't going to happen next month. I'm talking about the future. But where are we now? We're already at an amazing spot that a lot of people don't realize. Nobody should be shooting at f10 for deep sky objects and doing 10-minute exposures anymore. Here's some examples. 30-second exposure, take a bunch of them, 290 30-second exposures. You still need 2.5 hours of exposure. We're not breaking the laws of physics here. We're just taking advantage of the fact that the noise is lower than the signal and the exposure time can be shorter and the stacking will work because of it. Here's 30 seconds on the eyes, galaxies and Markarian's change. 30 seconds doesn't look very impressive. Take 3 hours to 30-second exposures. It looks great. Okay. Now, I've been talking about this for a long time, actually, because this is not as new as you think it is. This is 30-second subs of the Horsehead Nebula. It's only 2 hours worth of data. And it's with does that say a KAF 8300? Yes. That was the bread and butter CCD for a while. And if you've been around long enough, you know the 8300 was really hot stuff when it was new. But by today's standard, this is the worst CCD ever made. Not really. But it had really bad read noise. This was not a high performance CCD. But I was doing 30-second subs. What made the difference? Number one was shooting at f4. F4 is very fast. It concentrates the light. That signal was very strong on that sensor. I binned 2x2. One of the advantages of CCD over CMOS to this day is when you bin, you got lower read noise from the bin on the circuitry. Actually, there's 2 CMOS sensors that do hardware binning now, but I don't think they get the read noise benefit that CCDs did. But if you got a 455 or 571 and you're binning, it's in software. You're not getting any read noise advantage from that. But CCDs, you got a 2x reduction in read noise when you bend. And so I got a reduction in read noise from binning. I got a reduction in or an increase in signal to noise ratio because of my very fast focal ratio. And I only needed 2 hours worth of data. And it's an interesting story. I was down in Okeechobee with a big bunch of friends, and we decided we were going to have an imaging contest amongst ourselves. And I had a Paramount, very expensive mount, but you know, things go wrong with expensive mounts, and something was going bump in that mount, and I could not shoot more than 30 seconds without trailed stars. And I didn't have an auto guider because I was the big jock who does an auto guide. So what did I do? I said, well, how long can I go? I can't go more than 30 seconds. Fine, let's just take 30-second exposures and see what happens. And I would say this image is what actually started me on the trail of, you know what, if you've got a fast scope and, you know, low read noise, you don't necessarily have to have really long exposures to get a really good image. Here's some other examples. 30 seconds at f7, not a very fast focal ratio. Took this a few years back. Notice how dark it is underneath the Horsehead Nebula. A newer, better camera, also at f7. But look at all this stuff that's going on underneath the Horsehead Nebula, all that detail that was lost in the read noise and the dark pattern noise is now coming out. A friend of mine was shooting a globular cluster, and he had all this stuff around the globular cluster. And I'm like, what is this? What's in the optical path? It looks like there's something going on. It was flux nebula. And it was because we were picking up flux nebula where we're just not used to picking up flux nebula but it's there. And things are showing up. We're getting more detail because the read noise and the pattern noise is getting so low. Well, not only can we detect these things, but this has implications for our stacking algorithms and our approach to imaging as a whole. in that we don't have to have very long exposures. All right. So raise your hand if you're the guy in the audience going, yeah, but what about narrowband? Okay. What about narrowband? Let's see. Here's some 60-second exposures of M42 at f7, not a really fast focal ratio at f7. Now, you were right. Somebody's thinking it. You're right. Big deal, Richard. M42 is pretty damn bright. So, I'm not real impressed. Well, okay, how about the Rosette Nebula? The Rosette Nebula is also still pretty bright, but these are only 30-second exposures and came out really well. And this is a 3 nanometer HA filter, so it didn't let a lot of light through. The most thing that this one here impresses me the most, because what I know that you don't know is the individual subs. 1 minute, I couldn't see anything. The screen stretch on a 1 minute sub showed nothing. And I'm like, I was doing the experiment to prove a point. So it's like, let it run for a couple hours and let's just see what happens when I align it and stack it. And there it is. It's all there. Stacking works. And as your optics get faster, it shortens how long the shortest sub can be. As the camera noise goes down, it shortens how long the shortest sub can be. And I see a lot of calculators online that take into account sky brightness and this, that, and the other thing. And this is where the chef in me wants to speak out and say, you're not making a microwave dinner. You are making you got to taste the soup every now and then. What are you shooting? Are you shooting M42 because it's really bright? Are you shooting the Foxford Nebula because it's not very bright? I start, one of the things my friends do that annoys me, and I tell them this and they just laugh about it, is they're always like, hey, can you come over here and look at this when you get up and going? And I'm like, yeah, that'll be about an hour. And they're like, why? You know what you're doing. It's like, no, I need to take a picture and I need to look at it and I need to move and I need to frame it up the way I want it. And then I need to say, okay, can I get away with 2 minute exposures? Oh, it's starting to trail. Okay. Now, do I want to spend all night diagnosing my auto guiding and my mount PEC, or do I want to get an image at the end of the night? My answer is I want an image at the end of the night. And if I can only go 2 minutes, I would rather just take 2 minute exposures and then go have some hot chocolate or help my friends image and whatnot. And so same thing, when you're imaging, you have to think about what you're shooting. You have to think about where you're shooting from. Am I shooting from my backyard in, outside Orlando, Florida, or am I shooting from down in Okeechobee, or am I at the Grand Canyon at, 7,000 feet and, Bortle almost zero skies? And am I shooting something very bright or something very dim? Anyway, you have to take that into account. So where are we now? The mostly now. I like the Starship. It's got a lot of promise. It almost works. And so it's a good image for what almost works. Kind of like where are we now? Most scopes, even f7, which is getting to be pretty slow. But if you're at f7 or faster and you're shooting one-shot color, you probably don't need to guide. Almost no matter what you're shooting, you probably don't need to guide. You can just see how long you can go. Really, if you can go 30 seconds or 45 seconds even on a cooled one-shot color camera, almost anything you're shooting, you just need to go. You can get as much data as you just need more exposures to collect the data. You don't need a long individual exposures. If you're doing LRGB, you probably don't need to guide. LRGB actually has a slight signal to noise improvement over most one-shot color cameras. They're getting really good with those dyes. A few years back, I would always say one-shot color is a fundamental handicap. The filter in front of a mono lets through more light than the filter on the color chip does. So the Bayer matrix drops the quantum efficiency. That's starting to not be true anymore. And in a couple of years, it probably won't be true for anything that's new on the market. But still, LRGB collects a lot of light, and you probably don't need to guide. It does depend on your focal ratio and what you're shooting. If you're shooting narrowband, try it. You'd be surprised what you can get, especially with HA. Now, O3 and sulfur, maybe. And the reason is most objects are much dimmer in O3 and sulfur than they are HA. There's a couple of exceptions to that. Thor's helmet, I think Thor's helmet is even brighter in O3 than it is HA. The Propeller Nebula, really bright in sulfur compared to even HA and O3. In time, nobody will be guiding. And a cooled camera really, really helps. You need to get that dark current down. Modern CMOS, the dark current is very, very low as long as you're cooling the sensor. You don't want to cool it ambient, especially if you live here in Florida. I won't even shoot with the DSLR in the summertime, maybe for Milky Way shots. But deep sky, just forget about it. So that's kind of like where we are mostly now. You probably don't need to guide. And it depends on what you're shooting, of course, and what telescope you're using. And I'm talking about deep sky stuff. The Lucky Imagers shooting the moon and the sun, they figured this out a long time ago. Just take 10,000 frames, throw out the bad ones and stack them. So again, they've been ahead of the curve for a while. It's just now deep sky is going to catch up with them because we can get the, on a bright target like the sun or the moon or the planet, you get so much signal, even at f30, you get so much signal that you can get away with these short exposures. Where are we going? In the future, the marriage of life stacking and computational photography is going to change things. Everything is going to be, as the sensitivity increases, read pattern and noise, dark noise is plummeting. QE is near the max. Your main imager can be the guider, and you don't even need to guide between every frame. You can just like periodically recenter or periodically move around in a zigzag pattern or do a little spiral or something for your so that your sigma reject will get rid of everything. You do want to move around a little bit. If you're just moving in one direction, you get walking noise. So that's something you got to fix too. Computers are getting faster, storage is getting cheaper, and software is getting cleverer. Software guiding needs to die. Wait a minute. I think my slides are messed up. I've got some duplicate slides. Let's try. Yes, here we are. Questions? Q&A. I'll give you some Q&A. Anybody want to ask me questions, or am I over and you want me to shut the heck up?
That was great. Thank you.
You're welcome. I like talking about this, so it's easy. And my wife doesn't want to hear it. So
what's your take? What's your take on Russell Cronin's new algorithms, Blur Exterminator, and his whole series of PixInsight tools?
Good stuff. Yeah, it's good stuff because he's not cheating. Topaz Noise cheats. He's not cheating. All he's done is he's made the computer do exactly what I do, only faster. So, if I was processing that data myself in PixInsight, I'd go through all these iterations and I would do this and that, and I would get a nice noise-free image at the end of the day. And that's really all his AI is doing, is it's cleaning up that image it was trained on cleaned up data. There are a lot of AI and denoising things that will go out. You see these, the Facebook ads with the pixelated face, and then it's all beautiful and you can see the freckles and everything. That's doing a lot of interpolation and filling in, and sometimes it goes out. One of the Galaxy, Samsung got in trouble. One of the Galaxy phones, if you took a picture of the moon, it went, this is a picture of the moon. It looked at a bunch of moon pictures, found one that looked exactly like it, and then blended it with your image. That's not AI. That's not photography. I'm going to sound like one of those old guys. That's not photography. You're cheating. I think that's cheating. What Russell Cronin's doing is not cheating. They're pretty good. I bought them. I use them. It saves me a lot of time. It doesn't do anything I wouldn't have done already, but I can do it now in 30 seconds instead of an hour. I'm a big fan of doing things in 30 seconds instead of an hour.
On your Horsehead Nebula photo where you showed the f7 and it was really dark at the bottom, then you went to a different camera. What's the newer camera you're using, that one-shot color cool camera?
So for some reason my internet went out and I missed most of your question.
When you were showing the difference in the Horsehead Nebula, when you went from f7 to another f7, but a different camera, and you have a one cooled camera. What camera?
So I went from the one was a Canon EOS RA modified DSLR. I've stopped using that on a telescope. It's great for nightscapes. Shoot the Milky Way, the nebula show up. I love that, but on a telescope, not so much. I'm using the new Horsehead was with a QHY 128C. It's a full frame Nikon chip, and it's cooled and does a wonderful job. I've lately started experimenting with a cooled 533 from Player One. Even better. Yeah.
So you mentioned summertime shooting, you wouldn't go out with like a Nikon camera, even if it was astro modified. You really feel strongly that the cooling is a must.
Yeah. So I've gone outside before at 11:30 at night and water's dripping off my nose and it's 93 degrees. So depends on where you live. If you're in Alaska, have at it. Of course, I don't know. It may get hot in Alaska right now, but it gets hot here in the summer, and the camera heats up, and it's just awful. And you can't calibrate it because some of the none of the frames are at the same temperature, so it doesn't calibrate very well. People do it, and they get really great results. And my only response to that is they had to work way too hard. I just want clean data. Clean data is very easy to process, and a cooled, regulated camera. Even if you can't cool it very much, the fact that all your frames are at a consistent temperature really helps a lot when you go to calibrating it with your darks, biases, and flats, that sort of thing.
Thank you.
Mm-hmm.
You mentioned the issue with shooting darks and biases at the same time. My understanding was it's different whether you're using a DSLR or a dedicated cooled camera, which one you're doing.
So the difference is if you shoot it, some software will take a bias and a dark, and what they'll do is they'll stretch the dark. So you might have a 10-minute dark and a 5-minute exposure, and so it'll use that bias to try to scale the dark. So biases and darks are used when you want to scale the dark, and that applies to any kind of camera if you want to scale the dark. I don't like scaling darks on a DSLR or any other camera. It's not really accurate. I feel like if you have a cooled camera, there's no excuse for not having darks that are at the same temperature, because you can set the temperature and take the darks in your office or in your bedroom or wherever you want. Most of the last couple of CCDs and all of the new CMOS, you don't need darks anyway. You just do a bias. That's all you have to do is the bias. But what happens is that the bias is the dark pattern noise, and the dark is also dark pattern noise and other noise. And if you take a dark, it has both types of noise in it. And if you take a bias and subtract it from the dark, it gets rid of, it subtracts out some of that pattern. But if you have the bias and a dark that has that bias in it, because you haven't subtracted it, you're literally subtracting the bias pattern twice. And so instead of being like a plus pattern, now it's a minus pattern, but it's still, you basically kept that noise there. So the only time you use, let me just summarize because I'm blathering. The only time you use a bias and a dark is if you're scaling your darks. And I don't recommend scaling darks. It does work mostly. It's fine. I'm not saying you shouldn't. It's not something I want to do just because I don't like to. But all you need are biases or darks, unless you're scaling your darks.
Okay.
Question on the quantum efficiency. So
Look up again if there's another question.
The really good, high quantum efficiencies in the green, really green part of the spectrum, but they all die by the time they get to the reds, or there's very little infrared. Are there any sensors that are pushing into the red more?
Yes. I'm going to look up over here on my other computer which one it is. So yeah, when you see the QE graph, the camera is not the efficiency of converting photons into electrical signal depends on the wavelength of the light. And let's see, the camera I'm looking for is my Neptune. I have a Neptune 2 from Player One, and it is so sensitive in the infrared that when I put an infrared pass filter on it, I can actually ignore the Bayer matrix, because you don't get the Bayer matrix at all. All you get is a black and white image. Your software has to do that. It's the IMX 464. That one has a really good infrared response. You can use it with methane as well, so it's good for that. QHY's got one too. I think Christopher Go was just talking about it recently. It may be the same sensor or a different one, but there's a couple of them on the market that have really good far red and infrared sensitivity. Some of them are, it's a color camera, but at those wavelengths, the Bayer matrix is transparent. So you don't get any modulation from the Bayer matrix at all. And so there's no color because the infrared just comes right through. And so you can ignore the Bayer matrix and you actually have just a solid monochrome image that you can use for other things. I've got a couple of IR pass only filters, and that's fun to play with.
No, you seem to be discouraging auto guiding, at least to the extent that it's going to die off in the future, hopefully. And I note that ZWO came out with a new camera that has built-in self-guiding. What's your thought on that?
Well, SBIG tried this 20 years ago. It has some pitfalls. One was the guider camera was behind the filter. So that was like the worst thing that they did. If you have a monochrome camera, and even if it's a monochrome guide camera, you put a HA filter in front of it. It's hard enough to find a good star to focus on with an HA filter, much less to find a guide star off axis with that. I believe they're marketing it for one-shot color cameras. So they're like, okay, this was the big problem with SBIG. We're just going to make one-shot color cameras with a monochrome guider. The monochrome guider is very sensitive, and you don't have a filter wheel, so it should work. So if you're shooting one-shot color and you want to guide, that camera will do it. And I don't know that I'm discouraging guiding. It's just, guiding is more work. It's one thing. It's something that can go wrong, and I just want to get rid of it. I don't want to guide. I would just, it's so nice to go unguided. I wrote scripts for the sky that would move the scope between exposures so I could still dither when I wasn't guiding. When you do the meridian flip on a German equatorial mount, you just plate solve back to where you are. You don't have to worry about finding the guide star. If you're dithering while guiding, you move the star and then you have to wait for the star to settle before you start imaging again. So duty cycle wise, it's more efficient to just, take a whole stream of exposures. So it's needless most of the time. I was guiding last month at a star party. It depends on what you're doing. I'm not saying you should never guide. I'm just saying I prefer not to when I can get away with it. But I still have to guide every now and then as well, just like anybody else. Depends on what I'm doing. But the day will come when nobody's guiding anymore. And that's probably, 5 to 10 years down the road, maybe 5 years, closer to 5 than 10, I think.
Okay, we have a question in here from Lawrence Feltz asking, new harmonic drives have significant periodic error because of their design, and the manufacturers recommend guiding with those mounts. Do you agree?
Funny you should ask. In the Sky and Telescope you guys were showing at the beginning with Stellafane, there is a review of the Rainbow Astro 135 mount written by me. And so I used it, and we always have to have what we liked and what we didn't like. And so, because, to be fair, insider, right? You can't say, oh, I loved it, it was wonderful. We have to be, to show how even-handed we are, we have to come up with something that we didn't like. Well, on the Rainbow Asteroid, I did not have to try very hard to come up with something I didn't like. I really hated the periodic error. I could not do even 10-second exposures consistently with that thing. The periodic error was so bad. But I did get some nice images of M13 without guiding because I took 5-second exposures. And M13 is a nice bright globular cluster, and I didn't need to guide. But I had to guide with it, and guiding worked just fine. Now, they do have a version of that with encoders where the periodic error is very small. And I think that in time, the periodic error on the harmonic mounts will get better. So the periodic error on them is going to get better, and the cameras are getting better to where you don't need long exposures. If I had one right now, actually, I still have the 135. You're going to want to guide for deep sky stuff most of the time, unless it's a really bright object and you want to shoot 5-second exposures. You're going to want to guide. I still love the mount though, for visual astronomy, for a travel scope. Really, really nice because of no counterweights. I cannot stress how much you are going to hate counterweights if you try to take a mount with you on an airplane. So it's great for visual. It's also great for lucky imaging. So shooting the sun, the moon, and the planets with it with a high-speed camera, periodic error really doesn't matter at all with that. So the harmonic mounts, whether it's Rainbow Astros or ZWOs, you do have to guide for deep sky stuff. You don't have to guide for anything else. You don't have to guide if you're doing visual with it. But they have some nice advantages.
All right, thank you. Just checking the chat here, see if anybody has anything else. I do not see any more questions.
Okay.
I think we're covered.
All right. Well, it's been fun. Thanks for having me.
Thank you very much.
That was great. I mean, I really picked up a lot of stuff. I'm not an astrophotographer, but it's interesting to see, to me, where the technology is going and how far we've come. You particularly showing those old hard drives, the bottomless pit of the 40 megabyte drive. I mean, that's definitely a sachet down memory lane. So
yeah.
Again, thanks to Lou for finding you, Richard, and for you to come and at the drop of a hat and just say, yeah, I'll absolutely, I'll talk to you guys. So we really appreciate that. And again, next month, we're going to be on Zoom as well. So we'll do this all again. And then I guess our next live in person meeting will be the Bob Meadows Stellafane report. So we'll do it then. So for that, let's stick a fork in this one and thank everybody for joining us. And we'll see you all next month. Thank you, Richard. Thanks, everyone. Bye-bye.
Right,
Thank you.
bye-bye.
Thank you very much.